Around 3500 BC in the fertile marshlands between the Tigris and Euphrates rivers, archaeological evidence reveals agricultural systems so sophisticated that they challenge our understanding of prehistoric farming capabilities. Recent excavations at es-Sawwan and Eridu have uncovered irrigation networks that demonstrate mathematical precision in gradient calculations, storage facilities with advanced preservation techniques, and administrative tablets documenting crop rotation systems that would not be rediscovered until the agricultural revolution of the 18th century AD. These discoveries present a fundamental puzzle for conventional archaeology. How did the earliest urban farmers possess knowledge that supposedly took millennia to develop? The cuneiform tablets from and Nippur, carefully catalogued in the British Museum and University of Pennsylvania collections, describe agricultural procedures with technical specificity that exceeds simple farming knowledge, incorporating astronomical timing, chemical soil enhancement, and hydraulic engineering that suggests access to advanced systematic understanding. Perhaps most intriguing are the tablets that reference divine agricultural instruction, describing beings called the Abgalu who taught humanity the fundamental principles of cultivation, irrigation, and land management. These texts present farming not as gradual human innovation, but as transmitted knowledge from technologically sophisticated sources. The archaeological evidence from Sumerian agricultural sites consistently supports these textual accounts, revealing capabilities that appeared fully formed rather than developing through observable stages. What emerges from careful examination of this evidence is a portrait of ancient agricultural life far more complex and sophisticated than conventional models suggest, operated by farmers who possessed knowledge systems that enabled them to transform hostile marshland into the breadbasket of civilization. The pre-dawn activities of Sumerian farmers centered on irrigation management systems that demonstrate remarkable engineering sophistication. Archaeological excavations at Girsu conducted by French archaeologist Ernest de Sarzec between 1877 and 1900 uncovered canal networks with gradient calculations precise to within millimeters per kilometre, requiring surveying capabilities that exceed documented ancient measurement tools. Administrative tablets from the site describe water allocation schedules tied to astronomical observations, with flow rates adjusted according to lunar phases and seasonal stellar positions. The canal system at Girsu extended over 42 kilometres, incorporating primary distribution channels, secondary feeder canals, and tertiary field networks that delivered water with mathematical precision to thousands of individual agricultural plots. The main canal maintained a gradient of precisely 2.3 mm per metre across its entire length, a consistency that required surveying accuracy approaching modern civil engineering standards. This precision becomes even more remarkable when considering that the canal was constructed during the early dynastic period around 2900 BC, predating the supposed development of advanced surveying techniques by over 4 millennia. Tablet AO 4356 from the Louvre collection, discovered during the Girsu excavations, contains detailed operational instructions for canal management that reveal the sophisticated knowledge required for daily water distribution. The text describes procedures for calculating optimal flow rates based on lunar phase observations, with specific adjustments required during the waxing and waning periods. The instructions specify that during the full moon period, flow rates should be reduced by approximately 1/8 to account for increased plant water absorption, while during the new moon rates should be increased proportionally. This correlation between lunar cycles and plant physiology demonstrates understanding of biological rhythms that would not be scientifically validated until 20th century agricultural research. The surveying techniques required to establish these precise gradients have puzzled modern engineers who have studied the Sumerian canal systems. Dr. Robert Adams of the University of Chicago, whose extensive fieldwork in southern Iraq during the 1960s documented hundreds of ancient canal traces, noted that the consistency of gradients across vast distances could only be achieved using sophisticated levelling instruments and trigonometric calculations. The Sumerians left no explicit descriptions of their surveying equipment, yet the physical evidence demonstrates they possessed capabilities equivalent to modern theodolites and laser levels. The water distribution schedule preserved in administrative records from Girsu reveals organisational complexity that coordinated thousands of farmers across the entire canal network. Tablet designations such as ITT2/0967 and ITT3/05321, housed in the British Museum, document rotating access schedules that ensured equitable water distribution while maintaining optimal flow rates throughout the system. These schedules incorporated variables including field size, crop type, soil conditions, and seasonal requirements, processed through mathematical algorithms that modern irrigation engineers recognize as optimization formulas. The astronomical component of irrigation management becomes apparent through analysis of the observation posts discovered at major canal junctions. Archaeological remains at these sites include stone platforms with precise cardinal alignments and marking systems that tracked stellar positions throughout the night. The tablets indicate that specific constellations visible at particular times determined the opening and closing of canal gates, creating an automated scheduling system based on celestial mechanics. The constellation known as the Field, corresponding to the modern square of Pegasus, served as the primary timing reference for autumn irrigation, while the hired man, identified as Ores, governed spring water distribution. Chemical analysis of canal sediments has revealed another dimension of Sumerian irrigation sophistication. Mineral deposits at specific points in the canal network show concentrations of nutrients that were deliberately introduced to enhance water quality for agricultural purposes. These mineral treatments included calcium carbonate, potassium salts, and trace elements that modern agricultural science recognizes as essential for optimal plant growth. The quantities and ratios of these additives suggest systematic water quality management based on detailed understanding of plant nutrition requirements. The massive granary complex at Uruk, excavated by the German Oriental Society beginning in 1912, reveals storage technologies that maintained grain viability for periods exceeding 30 years, according to residue analysis. The facilities incorporated ventilation systems with precise airflow calculations, chemical preservation treatments using mineral compounds, and architectural designs that regulated temperature and humidity without mechanical equipment. The Uruk granary complex, designated as Building Level 4A in the archaeological record, covered an area exceeding 3,000 square meters and contained storage capacity for approximately 12 million litres of grain. The structure's walls, constructed from mud brick with a thickness of 2.7 metres, incorporated internal channels that created convection currents, maintaining stable internal temperatures despite external fluctuations exceeding 30 degrees Celsius between summer and winter. This passive climate control system required sophisticated understanding of thermodynamics and airflow mechanics to design and implement effectively. Carbon-14 dating of grain samples from sealed storage compartments within the complex yielded dates spanning from 2800 BC to 2750 BC, indicating continuous use over a 50-year period. More significantly, biochemical analysis of the grain itself revealed preservation states that indicated viable germination potential after storage periods approaching 3 decades. Modern grain storage technology typically limits viability to 5 to 7 years, even under controlled conditions, making the Sumerian achievement remarkable by contemporary standards. The ventilation system incorporated into the granary structure demonstrates engineering knowledge that anticipated principles not formally recognized until the 19th century. Each storage chamber connected to a network of vertical shafts that extended from floor level to roof height, creating temperature differentials that drove continuous air circulation. The shaft dimensions varied systematically according to chamber size, with mathematical relationships that modern engineers recognize as optimized for maximum airflow efficiency. Measurements taken during excavation revealed shaft diameters ranging from 15 to 45 centimeters, with larger diameters corresponding to deeper chambers in precise proportional relationships. Chemical residues found coating the interior walls of storage chambers indicate the application of preservative compounds that protected grain from insect infestation and fungal growth. Analysis conducted by the Max Planck Institute for the Science of Human History identified mineral components including sodium chloride, borax compounds, and plant-derived essential oils that modern entomology recognizes as effective pest deterrents. The application methods described in associated administrative tablets involved heating these compounds to create vapor treatments that penetrated the entire grain mass, a fumigation technique not supposedly developed until the 20th century. Administrative Tablet W20307 from the Vorderasiatisches Museum in Berlin contains detailed operational procedures for the Uruk granary that reveal the systematic management required to maintain such sophisticated preservation systems. The text describes daily inspection routines, weekly moisture content assessments, monthly ventilation system maintenance, and seasonal reapplication of chemical preservatives. The inspection procedures specified exact criteria for grain quality evaluation, including color assessment, hardness testing, and germination trials that functioned as quality control protocols. The architectural sophistication of the granary extended beyond functional requirements to incorporate astronomical alignments that influenced internal conditions. The structure's primary axis aligned precisely 14 degrees east of true north, corresponding to the rising position of Sirius during the summer solstice in the 3rd millennium BC. This alignment created specific lighting conditions within storage chambers that modern food science recognizes as beneficial for grain preservation, minimizing photochemical degradation while providing sufficient illumination for inspection activities. Tablet CBS 10673 from the University of Pennsylvania collection contains agricultural instructions attributed to Enki that describe crop rotation sequences, soil enhancement procedures, and pest management techniques with chemical precision. The text provides specific mineral ratios for soil treatment, timing calculations for planting based on stellar observations, and procedures for seed selection that demonstrate understanding of genetic principles. The tablet, discovered during excavations at Nipper between 1889 and 1900, presents agricultural knowledge in a format that combines religious invocation with technical instruction, a pattern typical of Sumerian knowledge preservation systems. The text opens with an acknowledgement of Enki as Lord of Wisdom and provider of the divine ME concerning agricultural abundance, then transitions into detailed technical procedures that demonstrate practical application of advanced principles. The crop rotation sequence described in CBS 10673 specifies a 7-year cycle that alternates cereals, legumes, and fallow periods in mathematically determined patterns. The sequence begins with barley cultivation in years 1 and 2, followed by chickpea or lentil crops in year 3, wheat in year 4, a legume rotation in year 5, barley again in year 6, and complete fallow in year 7. Modern agricultural science recognizes this rotation pattern as highly effective for maintaining soil fertility, controlling pest populations, and maximizing long-term yield sustainability. The nitrogen-fixing properties of legumes that make this rotation effective were not scientifically understood until the work of Justus von Liebig in the 19th century, yet the Sumerian system exploited these benefits 3,000 years earlier. The soil enhancement procedures detailed in the tablet specify precise mineral applications that demonstrate sophisticated understanding of soil chemistry. The text describes treatments using crushed gypsum at a ratio of 1 part gypsum to 16 parts soil for clay-heavy fields, applications of river silt combined with animal manure at specific ratios depending on existing soil conditions, and additions of ash from specific plant materials that provided particular nutrient profiles. Chemical analysis of Sumerian agricultural soils conducted by soil scientists from the University of Chicago revealed residual mineral signatures consistent with these described treatments, confirming that the procedures were actually implemented as documented. The timing calculations provided for planting operations incorporate astronomical observations of remarkable precision. The tablet specifies that barley planting should commence when the constellation known as the True Shepherd of Anu, corresponding to modern Orion, reaches its heliacal rising position in conjunction with specific lunar phases. The text provides correction factors for different latitudes within Mesopotamia, indicating awareness that optimal planting times varied geographically. These calculations required understanding of celestial mechanics, seasonal variation, and plant development biology that integrated multiple knowledge domains. Pest management procedures described in CBS 10673 demonstrate understanding of insect behavior and plant chemistry that enabled effective control without synthetic pesticides. The tablet describes preparation of deterrent compounds using crushed neem leaves, fermented garlic solutions, and mineral suspensions that were applied at specific intervals determined by insect life cycle stages. The text specifies application timing based on observations of insect behavior patterns, with different treatments for different pest species. Modern entomological analysis confirms that the described procedures would effectively control the primary agricultural pests affecting Mesopotamian crops. The seed selection procedures detailed in the tablet reveal understanding of genetic inheritance principles that anticipated modern plant breeding by millennia. The text instructs farmers to select seeds from plants displaying specific desirable characteristics, including robust growth, large grain heads, and early maturation, then to isolate these selected seeds from general harvests and maintain them separately for future planting. The procedures describe multi-generational selection programs that systematically enhance desired traits, creating what modern genetics recognizes as directional selection for beneficial characteristics. The tablet specifies maintaining separate seed lines for different soil conditions and climatic zones, demonstrating awareness that genetic optimization required environmental specificity. Analysis of barley remains from multiple Sumerian sites reveals selective breeding programs that systematically enhanced grain size, drought resistance, and yield capacity across documented periods spanning over 500 years. The genetic modifications demonstrate understanding of inheritance patterns and systematic selection criteria that required institutional knowledge preservation across multiple generations. Archaeobotanical research conducted by Dr. Naomi Miller of the University of Pennsylvania, examining barley samples from es-Sawwan, Uruk, and Nippur, has documented progressive changes in grain morphology that indicate deliberate selective breeding. Measurements of grain length, width, and mass from samples spanning from 3000 BC to 2500 BC show systematic increases in all dimensions, with average grain mass increasing from approximately 35 milligrams to 52 milligrams over this 500-year period. This 49% increase in grain size represents a rate of genetic modification that exceeds natural evolutionary changes by several orders of magnitude. The breeding program's sophistication becomes apparent through analysis of trait correlations within the archaeological samples. Larger grain size consistently appears in association with increased rachis toughness, preventing premature seed dispersal, and with earlier flowering times, allowing completion of the growth cycle before summer heat stress. Modern plant genetics recognizes these trait combinations as indicative of systematic selection programs targeting multiple characteristics simultaneously, a breeding strategy requiring institutional knowledge and multi-generational planning. Genetic analysis of ancient barley DNA extracted from carbonized seeds provides molecular evidence for the selective breeding programs documented in morphological studies. Research conducted at the Max Planck Institute for the Science of Human History identified specific genetic markers associated with domestication traits, that appeared with increasing frequency throughout the Sumerian period. The markers associated with non-brittle rachis, the characteristic that prevents wild barley from shattering upon maturity, reached near fixation by 2700 BC, indicating that Sumerian farmers had successfully converted a wild plant characteristic into a stable domesticated trait through systematic selection. The drought resistance improvements documented in Sumerian barley represent another dimension of the breeding program's sophistication. Analysis of root structure characteristics preserved in soil matrices from Tel Eder revealed progressive development of deeper, more extensive root systems across successive archaeological levels. Barley plants from earlier levels displayed root depths averaging 15 to 20 centimeters, while later samples showed root penetration to depths exceeding 35 centimeters. This architectural modification enabled plants to access deeper soil moisture during drought conditions, significantly improving crop survival rates during water stress periods. Administrative tablets from Lagash document the organizational infrastructure that supported these long-term breeding programs. Tablet designations such as DP423 and DP468, published in the Lagash archive volumes, describe seed distribution systems that maintained separate storage facilities for elite breeding lines distinct from general consumption grain. The texts specify that farmers selected for seed production responsibilities received additional rations and reduced labour obligations, indicating that specialised agricultural expertise was recognised and institutionally supported. These breeding specialists transmitted technical knowledge across generations through apprenticeship systems that ensured continuity of selection criteria and maintenance of valuable genetic lines. The yield improvements achieved through Sumerian breeding programs can be quantified through analysis of harvest records preserved in administrative archives. Tablets from the Ur three-period document barley yields, ranging from 900 to 1,200 litres per hectare in early records, increasing to 1,400 to 1,700 litres per hectare in later documents from the same agricultural regions. This 50 to 60% yield increase over approximately 2 centuries represents agricultural intensification that conventional models attribute to improved cultivation techniques. But the genetic evidence demonstrates that biological enhancement through selective breeding contributed substantially to these productivity gains. Sumerian agricultural calendars preserved on tablets from Nippur incorporate astronomical observations of remarkable precision, including calculations of the precessional cycle, planetary movements, and stellar positions that determined optimal planting and harvest times. The mathematical sophistication required for these calculations exceeded contemporary astronomical knowledge by substantial margins. The agricultural calendar known as the Nippur calendar, preserved in multiple tablet copies including Nifor 001 and Nifor 357 in the Istanbul Archaeological Museum, divides the year into 12 months named for agricultural activities and religious festivals, with intercalary months inserted according to astronomical calculations that maintained synchronization between lunar and solar cycles. The calendar system employed a 19-year metonic cycle, inserting 7 additional months at specific intervals to prevent seasonal drift, demonstrating understanding of the mathematical relationship between lunar months and solar years that the Greek astronomer Mitton would not formalize until 432 BC. The astronomical observations underlying the calendar system incorporated stellar phenomena that required sophisticated observational capabilities and mathematical processing. The calendar linked agricultural activities to heliacal risings of specific stars and constellations, with different stellar markers governing different phases of the agricultural cycle. The heliacal rising of the constellation known as the Hired Man marked the beginning of spring planting, while the rising of the Furrow constellation signalled autumn harvest timing. These stellar observations required tracking celestial positions with precision sufficient to predict rising dates weeks or months in advance, necessitating accumulated observational data spanning multiple years or decades. The most remarkable astronomical component of Sumerian agricultural calendars involves their incorporation of precessional calculations. Tablet A06484 from the Louvre, part of the M. Ulapin Astronomical Compendium, contains star lists that include corrections for precessional drift, indicating awareness that stellar positions shifted gradually over extended time periods. The text specifies that certain agricultural timing markers required adjustment every 72 years to maintain accuracy, corresponding precisely to the 1-degree shift in stellar positions caused by axial precession. Recognition of this subtle astronomical phenomenon required continuous observational records spanning multiple centuries and mathematical capabilities for processing long-term positional data. Planetary observations integrated into agricultural calendars demonstrate knowledge of celestial mechanics that anticipated modern astronomy by millennia. The tablets describe Venus visibility cycles that govern specific agricultural activities, with different phases of Venus appearance and disappearance linked to particular farming operations. The Venus tablets of Amisaduqa, preserved in multiple copies including tablet K160 in the British Museum, document Venus observations spanning 21 years with mathematical precision that enabled prediction of future appearances. The astronomical calculations underlying these predictions required understanding of synodic periods, orbital mechanics, and mathematical techniques for processing cyclical phenomena. The integration of planetary movements into agricultural planning appears in tablets describing optimal times for specific crops based on Jupiter and Saturn positions. Administrative texts from specify that date palm pollination should occur when Jupiter occupies specific positions relative to background stars, while barley planting should align with particular Saturn configurations. Modern agricultural research has discovered correlations between planetary positions and terrestrial weather patterns through mechanisms involving solar activity and magnetospheric interactions, lending unexpected credibility to these ancient agricultural astronomical associations. Bronze plowshares discovered at Lagash demonstrate metallurgical composition optimized for specific soil conditions, with alloy ratios that maximize durability while maintaining appropriate cutting-edge characteristics. Chemical analysis reveals manufacturing techniques that produce work-hardened surfaces and precisely controlled carbon content that were not officially rediscovered until modern metallurgy. The plowshares recovered from agricultural contexts at Lagash during excavations conducted by André Parrot between 1931 and 1933 exhibit metallurgical sophistication that challenges conventional understanding of ancient bronze working capabilities. Spectroscopic analysis performed at the Laboratoire de Recherche des Musées de France identified alloy compositions containing 87 to 89% copper, 9 to 11% tin, and trace additions of arsenic and lead in quantities ranging from 0.5 to 1.2%. This precise compositional control produced bronze with mechanical properties optimized for agricultural applications, combining hardness sufficient to penetrate compacted soils with toughness that prevented brittle fracture under shock loading. The manufacturing techniques employed to produce these plowshares involved processes that created work-hardened cutting edges while maintaining softer, more ductile body sections. Metallographic examination conducted by Dr. Paul Craddock of the British Museum revealed microstructural evidence of systematic cold working applied specifically to blade edges, increasing surface hardness by approximately 40% compared to as-cast conditions. This selective hardening technique required understanding that mechanical deformation of metal, crystal structures enhance strength and wear resistance, principles that would not be scientifically explained until 20th century materials science. The carbon content variations detected within individual plowshares indicate intentional carburization treatments that enhanced surface properties. X-ray diffraction analysis identified carbon-rich surface layers extending to depths of approximately 0.3 millimeters, producing case-hardened surfaces that combined wear resistance with underlying toughness. The carburization process required precise temperature control during heating in carbon-rich environments, followed by controlled cooling that preserved the beneficial microstructural modifications. Modern metallurgical science recognizes these procedures as sophisticated heat treatment protocols that require detailed understanding of phase transformations and diffusion kinetics. Different ploughshare designs corresponded to specific soil conditions encountered in various agricultural regions throughout Mesopotamia. Shares designated for clay-heavy soils near Girsu exhibited broader blade geometries with shallower cutting angles, while implements intended for sandy soils at sites near displayed narrower profiles with steeper angles. The systematic variation in tool geometry demonstrates understanding that optimal agricultural implements required matching design parameters to environmental conditions, a principle that modern agricultural engineering formalizes through soil mechanics calculations. Administrative tablets from Lagash, designated RT-C398 and RTC402, describe quality control procedures for ploughshare production that specified acceptable composition ranges, hardness requirements, and dimensional tolerances. The texts indicate that bronze workers underwent specialized training lasting multiple years, and that their products were systematically tested before distribution to farmers. The testing procedures included striking shares against stone anvils to assess brittleness, attempting to bend blade edges to evaluate toughness, and conducting field trials in various soil conditions to verify performance characteristics. The maintenance and repair protocols documented in agricultural texts reveal sophisticated understanding of metal fatigue and wear mechanisms. Tablets from Umma describe procedures for periodic annealing of ploughshares to restore ductility after extended use, followed by rehardening through controlled cold working. These thermal cycling treatments demonstrate recognition that repeated stress loading degraded metal properties and that systematic restoration procedures could extend implement service life. Modern metallurgical analysis confirms that the described treatments would effectively reverse fatigue damage and restore mechanical properties. Administrative tablets from Umma document soil testing procedures that evaluated nutrient content, drainage characteristics, and salinity levels using chemical indicator plants and mineral analysis techniques. The texts describe treatment protocols for different soil conditions that demonstrate understanding of chemical processes and geological principles. The soil evaluation system preserved in tablet designations such as UTI 3/1647 and UTI 4/2193 from the Umma archive employed biological indicators that functioned as living chemical sensors for soil conditions. The texts specify that the growth characteristics of particular plant species indicated specific soil deficiencies or toxicities, with detailed descriptions of diagnostic features that enabled farmers to assess soil chemistry without direct chemical analysis. The indicator plant known as the salt plant, identified as Salicornia species by modern botanists, was specifically cultivated in small test plots to evaluate salinity levels, with plant height, colour, and seed production quantified to determine salt concentrations. The classification system divided soils into 7 primary categories based on texture, drainage, and chemical characteristics. The categories ranged from heavy clay soils designated as strong earth to sandy compositions termed light earth, with intermediate classifications that modern soil science would recognize as corresponding to different positions on the textural triangle. Each soil category received specific treatment recommendations that addressed its limiting factors, demonstrating systematic approach to soil management that anticipated modern soil science by millennia. Salinity management represented one of the most critical challenges facing Sumerian agriculture, and the texts document sophisticated understanding of salt accumulation mechanisms and remediation strategies. Tablets from Umma describe procedures for identifying saline soils through visual inspection of surface crusts, taste testing of soil samples, and observation of characteristic plant stress symptoms. The texts specify that high salinity conditions required fallow periods combined with flooding and drainage cycles that leached accumulated salts below the root zone. Modern soil chemistry recognizes these procedures as effective remediation techniques that exploit the solubility of sodium chloride and other salts in irrigation water. The treatment protocols for nutrient-deficient soils incorporated organic amendments, mineral additions, and crop rotations designed to restore fertility. Tablets designated DP523 and DP541 from Lagash describe applications of decomposed plant materials at ratios of 1 part organic matter to 8 parts. Soil, additions of river silt rich in nutrients deposited during flood events, and systematic use of animal manure composted with plant residues. The texts specify composting procedures that required maintaining moist conditions and periodic turning of compost piles to accelerate decomposition, processes that modern agricultural science recognizes as optimizing microbial activity and nutrient availability. Drainage assessment procedures documented in the Yuma texts evaluated soil permeability through systematic observations of water infiltration rates. The procedures involved excavating test pits to specified depths, filling them with water, and measuring the time required for complete drainage. The tablets provide standard infiltration times for different soil categories, with slow drainage indicating clay-heavy compositions requiring different management than rapidly draining sandy soils. Modern soil science employs essentially identical procedures for determining hydraulic conductivity, confirming the validity of the ancient assessment methods. The mineral analysis techniques described in administrative texts involved preparation of soil suspensions, observation of settling rates, and examination of deposited materials. Tablets from Umma specify mixing soil samples with water in standardized proportions, allowing suspended particles to settle, and analyzing the layered deposits that formed. The texts describe interpretation protocols that correlated layer thicknesses with soil composition, providing quantitative assessment of clay, silt, and sand fractions. Modern soil texture analysis employs refined versions of these sedimentation procedures, demonstrating continuity between ancient and contemporary soil science methodologies. Chemical treatment procedures for alkaline soils incorporated gypsum applications that modern soil chemistry recognizes as effective for reducing sodium levels and improving soil structure. The tablets specify application rates based on severity of alkalinity symptoms, with quantities ranging from 1 part gypsum per 32 parts, soil for mildly affected fields, to 1 part per 8 parts for severely alkaline conditions. The chemical mechanism underlying gypsum effectiveness involves calcium displacement of sodium from soil, exchange sites, a process that Sumerian farmers exploited empirically without requiring theoretical understanding of ion exchange chemistry. Excavations at Uruk revealed residential complexes designed for agricultural work teams that incorporated ergonomic principles, optimal spacing for tool storage, and architectural features that facilitated coordination of large-scale farming operations. Administrative records describe labor scheduling systems that maximized efficiency through mathematical optimization of task allocation. The Workgang residential complex, designated as Area 4B in the Uruk excavation reports, covered approximately 1,200 square meters and contained standardized housing units arranged in organized blocks surrounding central courtyard spaces. Each housing unit measured 4.5 meters by 6 meters internally, providing 27 square meters of living space for individual families within the Workgang. The standardization of unit, dimensions, and the systematic layout demonstrate planned construction that optimize space utilization while maintaining functional requirements for agricultural laborers. The courtyard spaces integrated into the residential complex served multiple functions that facilitated Workgang operations. Archaeological analysis revealed that courtyard surfaces were paved with fired brick set in bitumen, creating durable work areas that remained functional during wet conditions. The courtyards contained built-in features including stone benches at ergonomically appropriate heights for tool maintenance activities, raised platforms for grain processing operations, and covered storage alcoves with dimensions optimized for agricultural implement storage. The spatial organization minimized movement distances between storage, maintenance, and assembly areas, demonstrating systematic efficiency optimization. Tool storage facilities within the complex incorporated security features and organizational systems that managed agricultural implement inventories. Archaeological remains included locking mechanisms on storage alcove doors, inventory marking systems using impressed clay tokens, and systematic arrangement of tools by type and size. Administrative tablets found within the residential context describe checkout procedures for tool distribution, maintenance schedules for implement repair, and accountability systems that tracked tool assignments to individual workers. The organizational sophistication rivals modern equipment management systems in industrial agricultural operations. The architectural features designed to facilitate work coordination included raised platforms in central courtyard locations that served as assembly points and information distribution centers. These platforms, constructed from fired brick and measuring approximately 2 meters square, provided elevated positions from which work gang supervisors could address assembled teams and communicate daily assignments. The acoustic properties of the courtyard spaces with surrounding walls creating sound-focusing geometries enhanced speech intelligibility and enabled effective communication with large groups. Administrative texts from Uruk designated TSS-91 and TSS-94 describe labor scheduling systems that allocated work gang members to specific tasks based on skill levels, physical capabilities, and task requirements. The scheduling algorithms employed mathematical optimization techniques that balanced workload distribution while ensuring that critical agricultural operations received appropriate labor resources. The texts specify calculation procedures that considered task duration estimates, worker productivity rates, and coordination requirements between interdependent activities. Modern operations research recognizes these procedures as early implementations of resource allocation algorithms that maximize overall system efficiency. The work gang organization incorporated hierarchical structures with clearly defined roles and responsibilities that enabled coordination of complex agricultural operations. Administrative tablets document positions including gang supervisors responsible for overall coordination, task leaders who manage specific operations, skilled specialists for technical procedures, and general laborers who performed routine activities. The texts specify selection criteria for supervisory positions that emphasized experience, technical knowledge, and demonstrated leadership capabilities. The compensation systems provided differential rations based on position and performance, creating incentive structures that motivated productivity and skill development. Training programs for work gang members ensured that specialized agricultural knowledge was transmitted systematically to new workers. Administrative records describe apprenticeship periods lasting multiple growing seasons during which trainees worked under experienced farmers while learning cultivation techniques, tool operation, and maintenance procedures. The texts specify competency assessments that evaluated trainee capabilities before granting full worker status, ensuring that work gang members possessed necessary skills for effective agricultural operations. The systematic cultivation of date palms documented in Sumerian texts required sophisticated understanding of pollination, grafting, irrigation requirements, and long-term crop management. Tablets from describe pollination procedures with timing precision and technique specifications that demonstrate advanced horticultural knowledge. Date palm cultivation represented one of the most technically demanding agricultural activities in ancient Mesopotamia, requiring knowledge systems that integrated botany, phenology, and long-term planning across the multi-decade productive lifespan of palm trees. Tablets from designated UET 3/0145 and UET 3/01. 6-7 contain detailed horticultural instructions that demonstrate sophisticated understanding of palm biology and cultivation requirements. The pollination procedures described in these texts reveal precise knowledge of palm reproductive biology and optimal timing for artificial pollination. Date palms exhibit dioecious reproduction, with male and female flowers occurring on separate trees, requiring human intervention to ensure fruit set in commercial plantations. The Sumerian texts specify that pollination activities should commence when female flower spathes begin opening, a brief window lasting only several days during early spring. The procedures describe climbing techniques for accessing the crown region where flowers develop, methods for collecting pollen-bearing male flower clusters, and application techniques for distributing pollen onto receptive female flowers. The timing precision required for successful pollination depended on careful observation of phenological indicators that signaled optimal developmental stages. The tablets specify visual characteristics of receptive female flowers, including specific color changes, spatial positioning, and morphological features that indicated pollination readiness. Modern horticultural research confirms that successful date palm pollination requires precise timing within a narrow developmental window, validating the sophistication of the ancient observation protocols. Grafting techniques documented in the texts enabled propagation of superior date palm varieties while maintaining desirable fruit characteristics. The procedures describe selecting offshoots from productive mother palms, preparing planting sites with appropriate soil amendments, and establishing young palms with irrigation regimes that promoted root development while preventing water stress. The texts specify that grafted palms required 7 to 10 years to reach productive maturity, demonstrating understanding of the long-term planning required for date palm cultivation. Irrigation management for date palms incorporated understanding of their specific water requirements across different developmental stages and seasonal conditions. Administrative tablets from Uruk document water allocation schedules that provided heavy irrigation during active growth periods in spring and early summer, reduced watering during fruit development, and minimal irrigation during winter dormancy. The texts specify adjustments to irrigation frequencies based on soil conditions, tree age, and fruit load, demonstrating sophisticated understanding of physiological water requirements. Pest and disease management protocols described in the texts incorporated biological observations and cultural practices that maintained palm health. The tablets identify specific insect pests, including scale insects and beetles that damaged palms, describe their life cycle characteristics, and specify control measures including manual removal, application of deterrent substances, and pruning of affected tissues. The pest management timing coordinated with insect developmental stages, demonstrating understanding of pest biology that enabled effective control through precisely timed interventions. Harvesting procedures for date fruits required careful timing to optimize fruit quality and storage characteristics. The texts specify harvest timing based on fruit color development, sugar content assessment through taste testing, and firmness evaluation through tactile examination. Different date varieties matured at different times throughout the late summer and autumn, requiring systematic monitoring and sequential harvesting of multiple varieties. The tablets document classification systems for harvested dates based on size, color, and ripeness stage, with different grades directed to different uses including immediate consumption, processing for storage, and seed production. The economic importance of date palm cultivation received extensive documentation in administrative archives that tracked production from individual trees, managed labor resources for cultivation and harvest, and allocated date products through distribution systems. Tablets from Uruk record yields from specific named palms, document productivity changes across multiple years, and correlate production levels with management practices. This detailed record-keeping enabled identification of superior varieties and optimization of cultivation techniques based on empirical performance data. The flood management infrastructure discovered along ancient watercourses demonstrates systematic landscape engineering that controlled seasonal inundations through coordinated dam systems, bypass channels, and retention basins. The scale and precision of these installations required surveying capabilities and hydraulic calculations that exceed conventional ancient engineering. Archaeological survey of ancient river courses in southern Mesopotamia conducted by Robert Adams and subsequent researchers has documented extensive hydraulic infrastructure that managed seasonal flooding across landscape scales spanning hundreds of square kilometres. The flood control systems integrated multiple engineering components, including levee systems along primary watercourses, diversion structures that directed excess flows into bypass channels, retention basins that temporarily stored floodwaters, and controlled release structures that metered water back into irrigation systems as flood conditions subsided. The levee systems, constructed along the Euphrates and Tigris rivers, extended for distances exceeding 100 kilometres in continuous segments, requiring massive labour investments and coordinated construction efforts. Archaeological remains indicate levee heights ranging from 2 to 5 metres above adjacent floodplains, with crest widths of 6 to 8 metres, providing stable platforms for maintenance access and emergency operations. The levee cross-sectional profiles incorporated engineered slopes that maximise stability while minimising material requirements, demonstrating understanding of soil mechanics principles that govern earthwork stability. The diversion structures that directed floodwaters into bypass channels represented critical control points within the flood management system. Archaeological investigation of these structures has revealed sophisticated engineering features, including weird designs that automatically diverted flows when water levels exceeded design thresholds, gate mechanisms that enabled manual flow control, and sediment management features that prevented channel clogging. The hydraulic design of these structures required calculations of flow rates, water velocities, and channel capacities that anticipated modern open-channel hydraulics by millennia. Retention basin systems provided temporary storage for excess floodwaters, reducing peak flows in primary channels and enabling gradual infiltration and controlled release. Survey data from the Nippur region documented retention basins covering areas exceeding 10 square kilometres, with storage volumes approaching 50 million cubic metres. The basins incorporated inlet structures that distributed incoming flows to prevent erosion, outlet structures that controlled release rates, and emergency overflow spillways that prevented uncontrolled breaching during extreme flood events. The systematic arrangement of multiple basins in series created cascading storage systems that progressively attenuated flood peaks. The surveying capabilities required to design and construct these flood control systems demanded precise elevation measurements across vast distances and accurate positioning of structures to ensure proper hydraulic functioning. The levee systems maintained consistent elevations along kilometres of alignment, requiring levelling accuracy approaching modern surveying standards. The diversion structures incorporated precise positioning relative to river channels and bypass routes, demanding coordinate control systems that extended across the entire flood management network. Hydraulic calculations underlying the flood control system design incorporated understanding of flow dynamics, channel capacities, and system interactions that modern engineering recognizes as applied fluid mechanics. Administrative tablets from Lagash contain numerical data that appears to represent flow calculations, including channel dimensions, velocity estimates, and capacity determinations. The mathematical relationships preserved in these texts correspond to equations that modern hydraulic engineering employs for open channel flow analysis, suggesting that ancient engineers possessed quantitative methods for hydraulic design. The maintenance requirements for flood control infrastructure received systematic attention in administrative records that documented inspection schedules, repair procedures, and seasonal preparation activities. Tablets from describe annual levee inspections conducted before flood season that identified weak sections requiring reinforcement, vegetation removal operations that prevented root damage to earthworks, and emergency response procedures for flood events that exceeded design capacities. The organizational systems that coordinated these maintenance activities across extensive infrastructure networks demonstrate sophisticated management capabilities. Archaeological remains of sesame oil production facilities at Tel Edda reveal sophisticated chemical processing equipment, including pressing mechanisms, filtration systems, and storage vessels designed to prevent oxidation. The production procedures described in associated tablets demonstrate understanding of chemical processes and quality control measures. The sesame oil production complex excavated at Tel Edda by Belgian archaeologists between 1970 and 1990 covered an area exceeding 400 square meters and contained specialized facilities for seed preparation, oil extraction, purification, and storage. The architectural organization of the complex reflected a systematic production sequence that optimized material flow while maintaining quality control at each processing stage. The facility layout demonstrates industrial organization principles that modern chemical engineering recognizes as essential for efficient batch processing operations. The seed preparation area contained stone mortars, with dimensions standardized to process specific volumes of sesame seeds, bronze implements for removing seed coats, and washing basins with drainage systems that separated cleaned seeds from debris. Chemical residue analysis conducted on the mortar surfaces revealed traces of sesame seed components, along with mineral compounds that functioned as cleaning agents. The presence of sodium carbonate residues indicates that alkaline washing treatments were employed to remove seed coat materials and reduce bitter-tasting compounds that affect oil quality. The oil extraction equipment incorporated mechanical pressing devices that applied controlled pressure to rupture seed cells and release oil while minimizing extraction of undesirable components. Archaeological remains included massive limestone pressing beds with precisely carved channels that collected expressed oil, wooden beam mechanisms that generated crushing forces through lever action, and bronze collection vessels positioned to capture oil as it emerged from pressing operations. The pressing bed channels incorporated subtle gradients that directed oil flow toward collection points, while allowing sediment particles to settle in upstream sections, demonstrating understanding of gravity separation principles. The pressing procedures described in Administrative Tablet TIM 9/54 from the Iraq Museum specify that sesame seeds should undergo preliminary heating before pressing to enhance oil recovery. The text indicates that heated seeds yielded approximately 25% more oil than unheated seeds, a finding that modern food science confirms through understanding that heating reduces oil viscosity and disrupts cell membranes. The specified heating temperatures, described in terms of visual indicators such as seed color changes and aromatic development, corresponded to temperatures that modern analysis identifies as optimal for maximizing oil extraction without degrading quality. Filtration systems within the production facility employed multiple stages of clarification that progressively removed suspended particles and sediments from crude pressed oil. The first filtration stage utilized coarse fabric filters that removed large particles and seed fragments, followed by settling tanks where finer particles precipitated under gravity, and final filtration through fine fabric or felted materials that produced clear oil. The settling tank dimensions and residence times described in production texts indicate understanding that particle removal efficiency depended on providing sufficient time for gravitational sedimentation. Chemical stabilization treatments prevented oxidative degradation that causes oil rancidity during storage. Tablets from Tel Edda describe additions of specific plant materials to filtered oil that functioned as natural antioxidants. Modern chemical analysis has identified that the described plant materials contain phenolic compounds and tocopherols that inhibit oxidation through free radical scavenging mechanisms. The quantities specified in the ancient texts correspond to concentrations that contemporary food chemistry recognizes as effective for extending oil shelf life. Storage vessel design incorporated features that minimized oil exposure to oxygen and light, the primary factors causing oxidative deterioration. Archaeological recovery of intact storage jars revealed narrow-mouth designs that limited air contact with stored oil, ceramic compositions with low porosity that prevented oxygen diffusion, and surface treatments with resinous materials that created additional oxygen barriers. The vessels were typically sealed with clay stoppers coated with bitumen, creating hermetic closures that modern food science recognizes as effective for long-term oil preservation. Quality control procedures documented in administrative texts specified sensory evaluation criteria, including color assessment, aroma characteristics, taste properties, and viscosity observations that enabled detection of processing defects or deterioration. The text describes standardized tasting protocols conducted by trained evaluators who could identify specific quality defects and trace them to particular processing stages. This systematic quality management approach demonstrates understanding that oil quality depended on controlling variables throughout the entire production sequence. Production records from Tel Adair tracked oil yields from specific seed batches, correlated processing conditions with product quality, and documented storage stability over extended periods. These records enabled identification of optimal processing parameters and provided empirical basis for continuous improvement of production methods. The record-keeping systems employed mathematical calculations that converted between different measurement units, tracked inventory levels, and managed distribution to various consumption centers. Cuneiform tablets from Drehem document livestock management systems that tracked genealogies, optimized breeding selections, and maintained health protocols for herds numbering in the thousands. The record-keeping systems employed mathematical techniques for population management and genetic selection that demonstrate sophisticated organizational capabilities. The administrative archive from Drehem, Ancient Pusrish Dagon, contains over 15,000 tablets documenting livestock operations during the Ur-3 period between 2100 and 2000 BC. These texts provide unprecedented detail regarding animal husbandry practices that manage cattle, sheep, goats, and pigs in systematic programs that optimize productivity while maintaining herd health. The scale of operations documented in the Drehem texts exceeded that of most modern commercial livestock facilities, with some tablets recording daily movements of over 1,000 animals through the administrative center. The genealogical record-keeping systems tracked individual animals across multiple generations, documenting parentage, birth dates, physical characteristics, and production histories. Tablets designated PDT 2/1347 and PDT 2/1401 contain multi-generational pedigrees for breeding stock that extend over periods of 15 to 20 years. The texts record offspring counts from individual breeding females, survival rates for different family lines, and correlations between parentage and desirable production traits. Modern livestock genetics recognizes this type of systematic pedigree documentation as essential for implementing effective selective breeding programs. The breeding selection protocols described in administrative texts specified criteria for identifying superior animals suitable for breeding purposes. The criteria included multiple characteristics evaluated simultaneously, such as body size and conformation, milk production for females, temperament and handling ease, disease resistance, and feed conversion efficiency. Animals that excelled in multiple categories received designation as elite breeding stock and were maintained in separate facilities with enhanced rations and specialized care. The systematic evaluation of multiple traits demonstrates understanding that optimal breeding programs required balanced selection across various economically important characteristics. Mathematical population management techniques enabled administrators to maintain appropriate herd structures that balance productive animals with breeding replacements. The tablets contain calculations that projected future herd compositions based on current age distributions, anticipated mortality rates, and planned culling schedules. These projections employed demographic modelling techniques that modern population biology recognises as essential for sustainable herd management. The calculations specified optimal ratios between breeding females, young stock, and mature animals destined for slaughter, ensuring continuous production while maintaining genetic diversity. Health management protocols documented in the Drihem archive incorporated preventive measures, disease surveillance, and treatment procedures that maintained herd health across large populations. Tablets describe regular inspections of animals to identify early signs of illness, isolation procedures for sick animals to prevent disease transmission, and therapeutic interventions using medicinal preparations. The texts specify particular treatments for different disease conditions, indicating that Sumerian herders could diagnose specific ailments based on symptom patterns and apply appropriate remedies. The disease surveillance systems tracked health incidents across the entire livestock population, enabling identification of disease outbreaks and implementation of control measures. Administrative records documented disease occurrence rates for different herd sections, seasonal patterns in disease incidents, and correlations between management practices and health outcomes. This systematic epidemiological approach enabled administrators to identify risk factors and modify management procedures to reduce disease occurrence. Nutritional management systems optimized feed allocation based on animal production status and physiological requirements. The tablets specified different ration formulations for lactating females, young growing animals, pregnant females, and fattening stock. The ration compositions incorporated multiple feed ingredients including barley, legumes, and fodder crops, in proportions that modern animal nutrition recognizes as providing balanced nutrient profiles. The texts indicate that feed allocations were adjusted seasonally to account for changing physiological demands and varying feed availability. The facility infrastructure supporting Drihem livestock operations incorporated specialized structures for different management functions, including breeding pens with enhanced security and monitoring capabilities, milking facilities with equipment for collecting and processing dairy products, fattening pens with feeding systems that promoted rapid growth, and isolation areas for sick animals separate from main herd facilities. Archaeological investigation of livestock management sites has revealed architectural features consistent with these functional specializations, confirming the sophisticated infrastructure described in administrative texts. The economic integration of livestock operations within the broader Sumerian agricultural system enabled efficient resource utilization through complementary relationships between crop and animal production. Crop residues and processing byproducts provided livestock feed, animal manure enhanced soil fertility for crop production, and draft animals supplied traction power for agricultural operations. Administrative texts document systematic management of these material flows, with tablets recording quantities of crop residues allocated to different livestock categories and volumes of manure distributed to specific agricultural fields. The Sumerian Farmer's Almanac, preserved in multiple copies across different periods, contained agricultural instruction embedded within literary frameworks that served as mnemonic devices for preserving complex technical information. Detailed analysis reveals that the text encodes astronomical timing, chemical procedures, and engineering specifications within apparently simple farming advice. The Farmer's Almanac, known from Sumerian copies dating from the Old Babylonian period around 1800 BC, but clearly based on much earlier traditions, presents agricultural knowledge in a literary format that facilitated memorization and oral transmission. The text employs a narrative structure in which a farmer instructs his son in proper agricultural procedures, covering the complete agricultural cycle from field preparation through harvest and storage. Modern analysis conducted by scholars including Samuel Noah Kramer and Miguel Seville has revealed that beneath the surface narrative lies systematically encoded technical information that required specialized knowledge to interpret fully. the astronomical timing information embedded within the almanac appears through references to seasonal indicators and celestial observations that determined optimal timing for agricultural operations. The text describes planting activities beginning when certain stars become visible at dawn, irrigation adjustments timed to lunar phases, and harvest operations coordinated with specific stellar configurations. Decoding these astronomical references requires knowledge of Sumerian constellation systems and understanding of the relationships between celestial phenomena and agricultural timing. The precision of timing information encoded in these apparently simple references enabled farmers who understood the system to implement sophisticated scheduling protocols. Chemical procedures for soil treatment and crop management appear encoded within instructions that specify particular materials and application methods. The text describes spreading various substances on fields using terms that modern chemical analysis reveals refer to specific mineral compounds and organic materials. The quantities specified, when converted from Sumerian measurement units, correspond to application rates that contemporary agricultural chemistry recognizes as appropriate for addressing particular soil deficiencies. The encoding of this chemical information within agricultural instructions enabled preservation of technical knowledge in forms that could survive as oral traditions even if written records were lost. Engineering specifications for irrigation equipment and field layout appear embedded within descriptions of proper farming procedures. The text describes plough configurations, irrigation channel dimensions, and field preparation techniques using standardized terminology that conveyed precise technical parameters to knowledgeable readers. The specifications include dimensional ratios, angular relationships, and sequential procedures that function as assembly instructions for agricultural infrastructure. Modern agricultural engineers analyzing these encoded specifications recognize them as systematic design parameters that optimize equipment performance and field productivity. The mnemonic structure of the almanac incorporated multiple literary devices that facilitated memorization while preserving technical accuracy. The text employs rhythmic patterns, repetitive phrases, and structured sequences that enabled oral transmission across generations of farmers. The narrative framework provided contextual associations that linked technical procedures to memorable stories, enhancing retention while maintaining the precise sequencing essential for successful agricultural implementation. Cognitive psychology research confirms that information embedded within narrative structures exhibits superior retention compared to abstract technical documentation. The multiple manuscript copies of the Farmer's Almanac discovered at different archaeological sites demonstrate remarkable consistency in technical content despite variations in literary expression. Tablets from Nippur, and Susa contain versions that preserve identical agricultural procedures within slightly different narrative frameworks, indicating that the core technical knowledge remained stable across geographic regions and time periods. This consistency across independent transmission lines validates the effectiveness of the encoding systems employed to preserve agricultural information. The social function of the Farmer's Almanac within Sumerian agricultural education becomes apparent through analysis of contexts in which tablets were discovered. Multiple copies have been recovered from Screwball School contexts, indicating that the text served educational purposes beyond simple agricultural instruction. Student copies contain practice exercises that demonstrate the text was used to teach both agricultural techniques and literary composition skills simultaneously. This dual educational function enabled efficient transmission of technical knowledge through established educational institutions. Modern application of information theory to analysis of the Farmer's Almanac reveals that the text contains information density substantially higher than apparent from surface reading. The compressed encoding of technical data within literary frameworks achieved information storage efficiency comparable to modern data compression algorithms. This sophisticated information management approach enabled preservation of extensive technical knowledge within relatively brief texts, that could be memorized and transmitted orally, ensuring knowledge survival through periods when written records might be destroyed or inaccessible. Excavations of residential areas at Ur uncovered sophisticated urban garden systems with irrigation networks, soil composition management, and crop selection indicating advanced horticultural knowledge. The gardens incorporated fruit trees, vegetables, and medicinal plants in arrangements that optimized growing conditions and facilitated efficient water usage. The residential district excavated by Leonard Woolley at Ur between 1922 and 1934 revealed that individual houses incorporated garden spaces averaging 30 to 50 square meters in area. These gardens were not simple pleasure grounds, but productive horticultural systems that supplemented household food supplies and provided medicinal plants for home health care. The archaeological evidence demonstrates that urban residents possessed horticultural knowledge comparable to that employed in large-scale agricultural operations, adapted to the constraints of limited space and urban environmental conditions. The irrigation system serving these urban gardens incorporated sophisticated water management technologies scaled to residential applications. Archaeological remains included ceramic pipe networks that distributed water from primary distribution channels to individual garden plots, control valves that regulated flow rates to different garden sections, and drainage systems that removed excess water while preventing soil waterlogging. The pipe systems employed graduated sizing with larger diameter mains feeding progressively smaller distribution lines, demonstrating understanding of hydraulic principles that optimized pressure distribution throughout the network. Soil composition management in urban gardens addressed the challenge that native soils in residential areas often suffered from compaction due to foot traffic and construction activities. Archaeological analysis of garden soil layers revealed systematic soil enhancement through additions of organic matter, river silt, and mineral amendments. The enhanced soils exhibited compositions distinct from surrounding native materials, with higher organic content, improved structure, and enhanced nutrient levels. Chemical analysis indicated that urban gardeners employed the same soil management principles documented in agricultural texts, adapted to small-scale applications. The crop selection strategies employed in urban gardens optimized productivity within space, constraints through intensive cultivation techniques and strategic plant combinations. Archaeological recovery of plant remains from garden context identified diverse species, including date palms, pomegranate trees, fig trees, onions, garlic, lettuce, cucumbers, and various medicinal herbs. The species diversity enabled continuous production across seasons, while the vertical layering of trees, shrubs, and ground-level plants maximized productive use of available space. Modern analysis recognizes these polyculture systems as sophisticated approaches to intensive horticulture that achieve high productivity per unit area. The fruit tree cultivation documented in urban gardens required long-term planning and investment that exceeded typical agricultural time horizons. Date palms required 7 to 10 years to reach productive maturity, pomegranates needed 3 to 5 years, and fig trees began substantial production after 4 to 6 years. The willingness to make these long-term investments indicates that urban residents maintained stable residence patterns and possessed confidence in property rights that enabled them to capture benefits of their horticultural investments. The intergenerational nature of urban gardening created living knowledge transmission systems where parents taught children horticultural techniques while tending family gardens. Medicinal plant cultivation within urban gardens provided household access to pharmaceutical preparations for treating common ailments. Archaeological identification of medicinal species including mint, coriander, fennel, and various aromatic herbs demonstrates that urban residents cultivated the raw materials for home health care. Administrative texts from Mur describe preparation methods for medicinal compounds using garden-grown plants, indicating that urban households possessed pharmaceutical knowledge, enabling them to process plants into therapeutic preparations. The garden layouts documented through archaeological investigation incorporated design principles that optimized microclimatic conditions and facilitated maintenance activities. Gardens typically oriented with longer dimensions aligned north to south, maximizing solar exposure while providing shade areas near walls. Water features, including small pools or basins, provided humidity and cooling effects while supporting aquatic plants. Pathways and working areas received paving or gravel surfaces that prevented mud formation and facilitated garden access during wet conditions. These design elements demonstrate systematic horticultural planning that addressed both productive and aesthetic objectives. The social functions of urban gardens extended beyond simple food production to include recreational activities, social gatherings, and cultural practices. Archaeological evidence, including built seating areas, decorative plant selections, and architectural elements, suggests that gardens served as outdoor living spaces where families conducted daily activities. The integration of productive and social functions created multifunctional spaces that enhanced quality of urban life while contributing to household food security. Agricultural tablets describe pest management strategies employing biological control methods, companion planting, and chemical deterrents derived from plant and mineral sources. The procedures demonstrate understanding of insect behavior, plant chemistry, and ecological relationships that enabled effective pest control without synthetic chemicals. The integrated pest management systems documented in Sumerian agricultural texts incorporated multiple control strategies that addressed pest problems through complementary approaches rather than relying on single interventions. Tablet Y, OS4/36 from the Yale Babylonian collection describes pest management protocols that combined cultural practices, modifying environmental conditions unfavorable to pests, biological controls, using predatory insects and parasitoids, physical barriers preventing pest access to crops, and chemical deterrents discouraging pest feeding or reproduction. The systematic integration of the multiple control methods demonstrates sophisticated understanding that effective pest management required comprehensive approaches addressing pest populations through various mechanisms. Biological control methods exploited natural predator-prey relationships to suppress pest populations below economically damaging levels. The texts describe encouraging populations of beneficial insects through habitat management practices, including maintaining flowering plants that provided nectar and pollen for adult predators, preserving hedgerows and field margins that offered shelter for beneficial species, and timing pesticide applications to minimize impacts on beneficial insects. Specific beneficial insects mentioned in the texts include ladybird beetles that preyed on aphids, parasitic wasps that attacked, caterpillar pests, and predatory bugs that fed on various crop-damaging insects. Modern entomology confirms that the species identified in ancient texts function as effective biological control agents in agricultural systems. Companion planting strategies utilized plant-plant interactions to reduce pest damage through multiple mechanisms. The tablets describe planting aromatic herbs among crop plants to mask attractive odors that pests use to locate host plants, incorporating plants that produce natural insect repellents within crop fields, and establishing trap crops that attracted pests away from main crop plants. The text specifies that onions or garlic planted among cereals reduced aphid infestations, that coriander grown near legumes deterred pod-boring insects, and that mustard plants established at field edges concentrated flea beetles away from primary crops. Modern agricultural research has validated that the companion planting combinations described in Sumerian texts exploit genuine biochemical and behavioral mechanisms that affect pest populations. Chemical deterrent preparations incorporated plant extracts and mineral compounds that repelled insects or inhibited their feeding and reproductive activities. The texts describe preparation methods for pest control compounds, including crushing neem leaves and steeping them in water to extract insecticidal compounds, fermenting garlic in oil to concentrate sulfur-containing deterrents, preparing pepper extracts that created chemical barriers on plant surfaces, and mixing wood ash with water to create alkaline solutions that desiccated soft-bodied insects. Modern chemical analysis of the plants and minerals specified in these preparations reveals that they contain compounds with documented insecticidal or repellent properties, including azadirachtin from neem, allicin from garlic, capsaicin from peppers, and alkaline salts from wood ash. Application methods for pest control preparations demonstrated understanding that effectiveness depended on achieving thorough coverage while timing applications to target vulnerable pest life stages. The tablets specify that liquid preparations should be applied using bundles of plant material dipped in solution and shaken over crop plants, that powder formulation should be dusted onto damp plant surfaces where they would adhere, and that fumigant treatments should be applied in enclosed spaces during evening hours when target insects were active. The texts indicate that application should target young larval stages, when insects were most vulnerable, and that repeat applications at specific intervals were necessary to maintain control as pest populations re-invaded treated areas. Pest monitoring systems enabled farmers to detect pest infestations early and implement control measures before populations reached damaging levels. The tablets describe regular field inspections conducted at specified intervals, systematic examination of plant tissues, where pests typically occurred, and documentation of pest abundance levels that triggered control actions. The monitoring protocol specified examining leaf undersides where eggs and young larvae concentrated, inspecting developing fruits and grain heads where later stage insects fed, and observing adult insect activity patterns that indicated reproduction was occurring. Modern integrated pest management employs essentially identical monitoring approaches, confirming the validity of ancient pest surveillance protocols. The understanding of insect life cycles documented in agricultural texts enabled timing of control interventions to target vulnerable developmental stages. The tablets describe pest development sequences including egg-laying periods, larval feeding stages, pupation phases, and adult emergence timing. The texts specify that control measures were most effective when applied during early larval stages before extensive feeding damage occurred, and that understanding generational timing enabled prediction of when pest populations would be present. This knowledge of pest phenology demonstrates systematic observation and documentation of insect development that enabled effective pest management planning. Administrative records document harvest scheduling systems that optimized grain collection based on astronomical observations, weather prediction, and crop maturity assessment. The precision of harvest timing and the coordination required for large-scale operations demonstrate sophisticated organizational capabilities and detailed agricultural knowledge. The harvest scheduling systems preserved in administrative archives from Umma and Girsu reveal mathematical optimization techniques that balance competing demands of crop maturity assessment, labor availability, processing capacity, and storage preparation. Tablet designations such as MVN 13/843 and MVN 15/217 document harvest planning procedures that began weeks before actual grain collection commenced, incorporating multiple data streams including astronomical observations, indicating optimal seasonal timing, field inspections assessing crop maturity progress, weather prediction systems, forecasting conditions during proposed harvest periods, and labour mobilisation schedules coordinating thousands of workers across vast agricultural territories. The astronomical timing component of harvest scheduling employed stellar observations that correlated with crop maturity patterns established through centuries of empirical observation. Administrative texts specify that barley harvest should commence when the constellation known as the Stars, corresponding to the Pleiades cluster, reached its acronautial rising position at sunset during late spring. This astronomical marker correlated with the approximately 130 to 140 days required for barley maturation after spring planting, providing a celestial timing reference that remained consistent across years despite annual variations in planting dates caused by weather conditions. The texts indicate that wheat harvest followed approximately 15 to 20 days after barley harvest began, a differential that modern agricultural science confirms reflects the slightly longer growing season wheat requires compared to barley. Crop maturity assessment procedures documented in administrative texts employed systematic field sampling protocols that evaluated grain development stages across multiple fields within agricultural territories. The tablets describe designated inspectors who conducted regular field visits during the final weeks before harvest, collecting grain samples from standardized locations within each field and assessing maturity characteristics including kernel hardness, moisture content, and ease of separation from chaff. The sampling protocols specified collecting samples from field edges where crops matured earlier due to enhanced sunlight exposure from central areas representing average field conditions and from lower areas where drainage conditions might delay maturation. This systematic sampling approach enabled accurate assessment of maturity distribution across entire field systems. The maturity evaluation criteria specified in agricultural texts demonstrate sophisticated understanding of the physiological changes occurring during grain development. The texts describe the progression from milk stage when kernels contained liquid endosperm, through dough stage when endosperm solidified but remained soft, to physiological maturity when moisture content decreased and kernels achieved maximum dry weight. The optimal harvest timing occurred during a narrow window after physiological maturity, when grain moisture content decreased sufficiently to enable efficient threshing, but before excessive drying caused shattering losses. Modern grain science recognizes this optimal harvest moisture content as approximately 15 to 18% for barley and wheat, and the ancient texts specify equivalent moisture levels through descriptive characteristics, including kernel firmness and audible properties when struck. Weather prediction systems incorporated in harvest planning enabled scheduling adjustments that minimize losses from untimely precipitation or extreme heat. The prediction methods combined astronomical observations, atmospheric indicators, and empirical patterns established through long-term weather record keeping. Administrative texts describe watching for specific cloud formations, monitoring wind direction changes, and observing animal behavior patterns that signaled approaching weather changes. The prediction systems distinguished between different weather phenomena, including brief thunderstorms that caused minimal harvest disruption, extended rainy periods that could damage standing grain, and hot, dry winds that accelerated shattering losses and required immediate harvest acceleration. Labour mobilization for harvest operations represented the most complex organizational challenge documented in administrative texts. The harvest period lasted only 2 to 3 weeks for each crop type, creating intense labour demand that exceeded the agricultural workforce normally maintained in farming communities. Administrative records describe systematic labour recruitment from urban populations, coordination with pastoral communities to provide temporary agricultural workers, and mobilization of corvée labour from populations owing service obligations to temple or palace institutions. Tablets document the movement of thousands of workers to agricultural districts during harvest periods, with detailed record-keeping of individual worker assignments, ration distributions, and tool allocations. The coordination of harvest activities across multiple fields required scheduling algorithms that optimized the sequence of field harvesting to match crop maturity patterns with available labour and processing capacity. Administrative texts contain mathematical calculations that determined optimal harvest sequences, considering factors including field location, relative to processing facilities, estimated yield levels affecting required labour time, and maturity assessment results indicating which fields required priority attention. Modern operations research recognizes these scheduling procedures as early implementations of constrained optimization algorithms that maximize overall system efficiency while satisfying multiple operational requirements. Quality control during harvest operations employed inspection systems that verified proper cutting heights, grain handling procedures, and field clearing standards. The tablets specify that grain stalks should be cut leaving stubble height of approximately 15 to 20 centimeters, enabling efficient collection while preserving stubble that would be grazed by livestock after harvest. Inspection protocols verified that cut grain was immediately collected and transported to threshing facilities to prevent losses from bird predation or weather damage. The systematic quality monitoring ensured that harvest operations maintained standards that maximized grain recovery and quality. Archaeological remains of threshing floors and processing facilities reveal engineered surfaces, specialized tools, and spatial organizations that maximized efficiency in grain processing. The designs incorporate understanding of mechanical advantage, material properties, and workflow optimization that enabled processing of massive harvest volumes. The threshing floor complexes excavated at multiple Sumerian sites demonstrates sophisticated engineering that optimized grain processing efficiency through systematic facility design. The threshing floors at Girsu covered areas exceeding 1,000 square meters in continuous paved surfaces with individual processing circles measuring 15 to 20 meters in diameter arranged in organized patterns that facilitated simultaneous operation of multiple threshing teams. The floor surfaces employed fired brick or compacted clay sealed with bitumen, creating hard, smooth, impermeable surfaces that prevented grain loss while enabling efficient sweeping and collection operations. The circular geometry of individual threshing areas reflected optimal spatial organization for the threshing technique employing draft animals, pulling threshing sledges over spread grain. The circular layout enabled animals to follow continuous paths without sharp turns that would reduce processing efficiency or cause equipment damage. The 15 to 20 meter diameter corresponded to optimal path lengths that maintained animal movement speed, while ensuring thorough grain processing across the entire threshing surface. Mathematical analysis of these dimensions reveals that the ancient designers understood geometric relationships that optimize the balance between processing area and animal path efficiency. The threshing sledges employed for grain processing incorporated engineering features that maximized mechanical efficiency in separating grain from chaff. Archaeological recovery of sledge fragments and analysis of wear patterns on threshing floor surfaces have revealed that sledges consisted of wooden platforms measuring approximately 1.5 meters by 1 meter, mounted on runners embedded with flint or chert chips that provided abrasive cutting surfaces. The weight of the sledge combined with the driver standing on the platform created downward pressure that drove the abrasive cutting elements through the grain stalks, crushing stems and loosening grain from seed heads. The sledge design represented a sophisticated application of mechanical principles that converted animal traction power into grain processing action through optimized weight distribution and cutting surface geometry. The processing sequence documented in administrative text describes systematic operations that progressively separated grain from chaff and straw through multiple stages. Initial threshing operations crushed grain stalks and loosened grain through repeated passes of loaded sledges driven by oxen or donkeys. Following initial threshing, workers using wooden forks tossed processed material into the air during windy conditions, exploiting differential aerodynamic properties that allowed wind to carry away lightweight chaff, while heavier grain fell back to the threshing floor surface. This winnowing process required understanding of material properties and fluid dynamics that enabled effective separation without mechanical equipment. The spatial organization of threshing complexes incorporated designated areas for different processing stages and temporary storage of materials at various processing levels. Archaeological investigation has revealed that complexes included receiving areas where harvested grain arrived from, fields, primary threshing zones where initial processing occurred, winnowing areas positioned to exploit prevailing wind patterns, secondary cleaning zones where additional separation of grain from remaining chaff occurred, and temporary storage areas where cleaned grain awaited transport to permanent storage facilities. The systematic progression through these functional zones minimized material handling distances and prevented mixing of materials at different processing stages. Tool specialization within threshing operations employed implements optimized for specific tasks within the processing sequence. Archaeological recovery and analysis of tool assemblages from threshing contexts have identified wooden forks with tine spacing optimized for winnowing operations, broad wooden shovels for moving large volumes of mixed grain and chaff, fine-tined rakes for final grain cleaning, and measuring vessels for quantifying processed grain volumes. The systematic tool sets demonstrate understanding that processing efficiency required matched implementation for each operational stage. The processing capacity calculations preserved in administrative texts reveal mathematical modelling of threshing operations that enabled planning of facility sizes and labour allocations. The tablets contain estimates of processing rates for different grain types under various conditions, calculations of labour requirements based on anticipated harvest volumes, and projections of processing time needed to complete harvest processing before seasonal rains threaten stored grain. These calculations employed mathematical techniques including rate estimation, capacity planning, and resource allocation that modern industrial engineering recognizes as fundamental operations management methods. Quality control during processing operations employed inspection protocols that verified complete separation of grain from chaff, removal of damaged or immature kernels, and achievement of cleanliness, standards required for storage. Administrative texts specify acceptable levels of chaff contamination in processed grain, typically less than 2 to 3% by weight, and describe systematic sampling and inspection procedures that verified quality standards. The quality management systems ensured that processed grain met storage requirements that would maintain quality during extended storage periods. Legal tablets from Lagash document water allocation systems based on mathematical formulas that ensured equitable distribution among farmers while maintaining canal system efficiency. The administrative procedures employed geometric calculations and flow rate measurements that required sophisticated mathematical capabilities. The water rights system preserved in legal codes and administrative texts from Lagash represents one of the most sophisticated resource allocation frameworks documented in ancient civilizations. The fundamental legal principle established equitable access to irrigation water based on field area cultivated, with proportional allocations calculated according to mathematical formulas that considered multiple variables including land area, soil type, crop water requirements, and position within the canal network. Tablet designations such as DP6-4 and DP6-7 from the Lagash archive contain detailed water allocation calculations that demonstrate systematic application of mathematical principles to ensure fairness while maintaining overall system functionality. The mathematical basis for water allocation employed geometric calculations that determined field areas requiring irrigation and converted these areas into volumetric water allocations based on crop-specific water requirements. Administrative texts describe survey procedures that measured field dimensions using standardized length units, calculated field areas through geometric formulas for regular and irregular plot shapes, and applied water requirement factors that varied according to crop type and soil conditions. The calculations for irregularly shaped fields employed triangulation methods that subdivided complex geometries into simpler triangular components whose areas could be calculated individually and summed to determine total field area. The conversion from field area to water volume allocations incorporated understanding of crop water requirements that varied across different growth stages and responded to seasonal conditions. Administrative tablets specified different water application rates for barley, wheat, legumes, and date palms, with rates expressed in volumetric units per area unit, that modern irrigation science recognizes as equivalent to application depth measurements. The texts indicate that allocation rates increase during active growth periods in spring and decrease during grain-filling stages in early summer, demonstrating understanding that crop water requirements varied systematically across the growing season. The position-based adjustments incorporated into water allocation formulas address the hydraulic reality that water delivery efficiency decreased with increasing distance from primary canal sources. Fields located near canal heads received higher priority access during periods of limited water availability, but received proportionally reduced allocations during abundant water conditions to ensure that downstream fields received adequate supplies. The allocation formulas employed correction factors that increased allocations for downstream positions to compensate for conveyance losses through seepage and evaporation. These position-based adjustments required understanding of hydraulic principles governing flow in open channels and quantification of loss rates across different canal segments. Flow rate measurement techniques documented in administrative texts enabled verification that actual water deliveries matched calculated allocations. The measurement methods employed timing, observations of water level changes in calibrated basins, creating volumetric measurements from known basin dimensions and observed depth variations. Administrative texts describe standardized measurement basins constructed at key distribution points throughout canal networks, with designated water measurers responsible for conducting measurements during distribution periods and recording results for administrative verification. The measurement protocols specified procedures for accounting for evaporation losses during measurement periods and corrections for temperature effects on water volume. The dispute resolution procedures established in legal text addressed conflicts arising from water allocation disagreements and provided systematic processes for adjudicating competing claims. Legal tablets describe cases involving accusations of unauthorized water diversion, disputes over allocation calculations, and complaints regarding inadequate water delivery to downstream positions. The resolution procedures employed mathematical recalculation of allocations based on verified field measurements, field inspections to confirm proper operation of distribution infrastructure, and penalties for proven violations of water allocation regulations. The systematic legal framework enabled stable operation of water distribution systems despite inherent potential for conflict over limited water resources. The institutional structures supporting water allocation systems included administrative positions responsible for allocation calculations, infrastructure maintenance, measurement operations, and dispute resolution. Administrative texts document water administrators who managed allocation planning, canal inspectors who monitored infrastructure condition and water distribution operations, and legal officials who adjudicated water rights disputes. The organizational hierarchy enabled coordinated management of complex distribution networks serving thousands of farmers across extensive agricultural territories. Administrative records describe coordinated agricultural activities across multiple cities involving synchronized planting schedules, shared resource allocation, and coordinated harvest timing. The level of regional coordination required communication systems and administrative capabilities that enabled landscape-scale agricultural planning. The regional agricultural coordination documented in Sumerian administrative archives demonstrates systematic planning that integrated activities across multiple urban centers and their associated agricultural territories. Tablets from Umur, Girsu, Lagash, and Nippur contain synchronized planting schedules, coordinated labor mobilizations, and integrated resource distribution systems that functioned at landscape scales spanning hundreds of kilometers. The coordination mechanisms required communication networks capable of transmitting information rapidly across these distances and administrative systems that could process complex logistical requirements involving thousands of farmers and millions of liters of grain. The synchronized planting schedules preserved in administrative texts reveal that regional coordination aimed to optimize overall agricultural productivity through temporal distribution of labor demands and risk mitigation through geographical diversification. The tablets indicate that northern regions typically initiated planting operations approximately 10 to 15 days earlier than southern areas, reflecting climatic gradients that created progressive maturation of growing conditions from north to south. This temporal offset distributed harvest labour demands across extended periods, enabling labour sharing between regions where peak demands occurred at different times. The synchronization also provided risk mitigation by ensuring that if adverse conditions affected one region during critical growth stages, other regions experiencing different timing might avoid similar damage. The shared resource allocation systems documented in administrative archives coordinated distribution of critical agricultural inputs, including seed grain, draft animals, and specialized equipment across multiple urban territories. Tablets from the Earthry period describe systematic movement of seed grain from areas with surplus production to regions requiring supplemental supplies, temporary transfer of draft animal teams to support ploughing operations in areas with insufficient local animal resources, and circulation of specialized equipment including threshing sledges and irrigation technology among communities that shared ownership of expensive capital equipment. These resource-sharing networks enabled more efficient utilization of limited resources while providing mutual support that enhanced agricultural security. The communication systems enabling regional coordination employed multiple mechanisms, including messenger services that transmitted information between administrative centers, signal systems that communicated simple messages rapidly across long distances, and regular administrative meetings where officials from different centers coordinated planning activities. Administrative texts describe professional messenger positions responsible for carrying sealed tablets between cities, with travel time estimates indicating that messages could traverse distances of 100 kilometers within 2 to 3 days. The reliability of communication networks enabled coordination of time-sensitive agricultural operations that required precise synchronization across distant locations. The harvest coordination documented in administrative texts achieved optimal processing of regional grain production through systematic scheduling that matched harvest timing with available processing capacity and storage preparation. Tablets describe regional harvest sequences that progressed systematically from southern to northern territories as crops matured, with mobile labour forces following the harvest progression and processing facilities operating continuously as grain arrived from successive harvest zones. This coordinated harvest system maximised processing efficiency, while ensuring that grain reached storage facilities before quality deterioration occurred. The regional storage and distribution networks integrated production from multiple territories into systems that balance local surplus and deficit through systematic grain movement. Administrative records document grain flows from high productivity regions to urban centres with large non-agricultural populations, redistribution of temple and palace grain holdings to support dependent populations, and maintenance of strategic reserves that provided security against localized crop failures. The storage network employed hierarchical structures with local granaries, collecting production from surrounding agricultural areas, regional facilities aggregating grain from multiple local sources, and central repositories managing reserves for entire political territories. The administrative infrastructure supporting regional coordination included positions at local, regional, and central levels that managed information collection, planning coordination, and implementation oversight. Tablets document agricultural administrators responsible for local planning and execution, regional coordinators who integrated activities across multiple centres, and central authorities who established overall policies and resolved coordination disputes. The hierarchical administrative structure enabled processing of complex information flows and decision-making across organisational levels appropriate to different planning scales. Excavations have revealed food preservation facilities employing drying, salting, and fermentation techniques that maintained food supplies through seasonal cycles. Chemical analysis of preservation residues reveals sophisticated understanding of food, chemistry, and microbiology that enabled long-term storage without refrigeration. The food preservation facilities excavated at and other Sumerian sites demonstrate systematic application of preservation techniques that exploited fundamental principles of food chemistry to prevent microbial spoilage and maintain nutritional quality. The preservation complex at covered an area exceeding 200 square meters and contained specialized facilities for different preservation methods, including drying chambers with controlled air circulation, salting stations equipped for brine preparation and dry salt application, fermentation vessels designed for controlled microbial processing, and storage areas with environmental conditions optimized for preserved product stability. The drying facilities incorporated architectural features that optimized air circulation and temperature control required for effective moisture removal. Archaeological investigation revealed that drying chambers contained raised platforms constructed from reed matting supported on brick pillars, creating airspaces beneath drying products that enhanced circulation and prevented moisture accumulation. The chambers included ventilation openings positioned to exploit prevailing wind patterns, with adjustable covers that enabled operators to regulate airflow according to external weather conditions and product moisture levels. The positioning of openings at different heights created convection currents that maintained continuous air movement through drying products. The drying procedures documented in administrative texts specified different protocols for various food products, reflecting understanding that optimal drying conditions varied according to product characteristics. Tablets describe that fish required rapid initial drying to prevent bacterial decomposition, achieved through exposure to direct sunlight and vigorous air movement, while fruits and vegetables required gentler drying at lower temperatures to prevent case hardening that sealed moisture within product interiors. The texts specify monitoring moisture content through tactile assessment and weight measurements, with dried products achieving target moisture levels of approximately 10 to 15% that prevented microbial growth while maintaining acceptable texture and flavor qualities. Salting preservation techniques employed both dry salt application and brine immersion methods selected according to product characteristics and intended storage duration. Archaeological recovery of preservation residues and analysis of ceramic vessels from preservation facilities have revealed that dry salting employed salt quantities typically ranging from 15 to 25% of product weight, creating osmotic conditions that extracted moisture from food tissues while establishing salt concentrations that inhibited microbial growth. Brine preservation employed salt solutions with concentrations typically ranging from 15 to 20% salt by weight, creating liquid environments that prevented oxygen exposure while maintaining antimicrobial salt concentrations. The chemical understanding underlying effective salting preservation appears in administrative texts that describe monitoring brine strength through flotation tests that assessed whether standardized objects floated or sank in prepared brines. The texts indicate that properly prepared preservation brines should float a fresh egg, corresponding to salt concentrations that modern food science recognizes as approximately 15 to 18%. This empirical testing method enabled consistent preparation of preservation brines without requiring chemical analysis equipment. Fermentation preservation techniques exploited controlled microbial metabolism that produced acids, alcohols, and other antimicrobial compounds while transforming food textures and flavors. Archaeological evidence of fermentation facilities includes ceramic vessels with capacity ranging from 20 to 100 liters, designed with narrow openings that limited oxygen exposure while enabling gas release during fermentation. Chemical analysis of residues from these vessels has identified organic acids, particularly lactic acid, indicating that fermentation processes employed lactic acid bacteria that converted carbohydrates into preservative acids while creating characteristic fermented flavors. The fermentation procedures documented in administrative texts demonstrate understanding that successful fermentation required controlling multiple variables, including temperature, salt concentration, oxygen exclusion, and process duration. The texts specify that fermentation vessels should be maintained in shaded locations that prevented excessive heating, that products should be submerged in brine solutions that excluded oxygen contact, and that fermentation processes required monitoring for approximately 7 to 14 days until desired transformation levels were achieved. The procedural specifications demonstrate empirical understanding of factors affecting fermentation outcomes, even without theoretical knowledge of underlying microbial processes. The integration of preservation techniques into agricultural planning systems enabled year-round food availability despite seasonal production patterns. Administrative texts document systematic allocation of fresh produce to preservation facilities during peak harvest periods, with preservation processing coordinated to match production volumes and storage capacity. The preserved product inventories documented in storage facility records provided supplies that bridged the period between successive harvests, ensuring continuous food availability through the annual cycle. Tablets documenting agricultural tribute collection reveal sophisticated economic systems that tracked production across multiple farms, calculated taxes based on land quality and yield potential, and coordinated redistribution to support non-agricultural urban populations. The mathematical and organizational complexity of these systems demonstrates advanced economic understanding. The agricultural tribute systems preserved in thousands of administrative tablets from Sumerian archives represent economic coordination mechanisms of remarkable sophistication that integrated production from dispersed agricultural territories into centralized distribution networks supporting urban populations. The tribute archives from Girsu alone contain over 4,000 tablets documenting grain collection operations during the Ur-3 period, providing unprecedented detail regarding the mathematical calculations, assessment procedures, and logistical operations required to transform distributed agricultural production into concentrated urban food supplies. Tablet designations such as ITT5/09876 and RTC409 document tribute calculations that incorporated multiple variables including field area measurements, soil quality assessments, historical yield data, and current season production levels. The field classification systems employed in tribute calculations divided agricultural lands into quality categories that reflected productive potential and determined expected tribute obligations. Administrative texts describe 7 primary land quality classes, ranging from prime irrigated lands designated as fields of the first water to marginal rain-fed areas classified as thin lands. Each quality class carried different productivity expectations, expressed as anticipated yield per unit area, with tribute obligations calculated as fixed percentages of expected production levels. The classification system required systematic soil evaluation, historical yield tracking, and periodic reclassification as land conditions changed through salinization, improved drainage, or other modifications affecting productive capacity. The mathematical procedures for calculating tribute obligations employed geometric area calculations combined with yield expectation factors and tribute rate percentages to determine grain quantities owed from individual fields. Administrative tablets contain detailed calculation sequences showing field dimensions measured in standardized length units, area computations using geometric formulas appropriate to field shapes, multiplication by yield factors specific to land quality classes, and application of tribute rates that typically range from 10 to 30% of expected production, depending on field ownership status and institutional obligations. The calculations demonstrate systematic application of mathematical operations including multiplication, division, and percentage calculations that required numerical literacy and computational capability. The assessment procedures documented in administrative texts incorporated field inspections that verified land classifications, confirmed crop cultivation, and evaluated growing conditions affecting actual productivity. Tablets describe assessment teams led by officials designated as field measurers, who conducted systematic surveys of agricultural territories, documented field dimensions and boundaries, evaluated soil conditions and irrigation adequacy, and estimated probable yields based on crop development observations. The assessment operations occurred at multiple times during growing seasons, with preliminary assessments during planting periods establishing baseline expectations and final assessments near harvest determining actual tribute obligations based on realized production. The flexibility mechanisms incorporated into tribute systems addressed the reality that agricultural production varied annually due to weather conditions, pest outbreaks, and other factors beyond farmer control. Administrative texts describe procedures for tribute reduction or forgiveness when documented crop failures occurred, with reduction percentages tied to severity of production shortfalls. Tablets from years experiencing regional drought document systematic tribute reductions of 30 to 50% for affected territories, demonstrating that tribute obligations adjusted to actual productive capacity rather than rigidly enforcing fixed obligations regardless of circumstances. The collection logistics documented in administrative archives required coordination of transportation, storage, and accounting operations that moved millions of litres of grain from dispersed agricultural fields to centralised storage facilities. Tablets describe systematic collection schedules that progress through agricultural territories following harvest completion, with designated collection points where farmers delivered tribute grain for measurement and recording. The collection operations employed standardised measurement procedures using calibrated vessels, official measurers responsible for accurate quantification, and witnesses who verified measurement accuracy to prevent disputes. The redistribution systems that allocated collected tribute grain to support urban populations incorporated sophisticated inventory management and distribution planning. Administrative texts document grain allocations to temple personnel, craft specialists, administrative officials, military forces, and dependent populations based on standardized ration scales that varied according to position and family size. The ration calculations employed mathematical formulas that converted personnel counts across different status categories into total grain requirements, compared requirements against available supplies, and adjusted allocation rates when supplies proved insufficient to meet full ration standards. The economic integration achieved through tribute systems created dependencies between agricultural producers and urban consumers that stabilized both sectors through mutual obligation. Farmers received security through institutional support during crop failures, access to specialized goods produced by urban craftsmen, and participation in religious and administrative systems centered in urban complexes. Urban populations obtained reliable food supplies through systematic tribute collection that pooled production risks across extensive agricultural territories and maintained strategic reserves that buffered against localized production shortfalls. The brewing industry documented in Sumerian texts represents sophisticated fermentation technology that produced standardized beer products in industrial quantities. Chemical analysis of residues from brewing vessels reveals precise control of fermentation conditions and ingredient ratios that demonstrate advanced understanding of biochemical processes. The beer production industry represented one of the largest manufacturing sectors in Sumerian economy, with administrative texts documenting production volumes exceeding millions of litres annually and labour forces dedicated to brewing operations numbering in the hundreds at major production centres. The economic importance of beer production derived from its role as a dietary staple, providing significant caloric content and essential nutrients, its function as a safe beverage alternative to potentially contaminated water supplies, and its use as a medium of exchange in ration distribution systems. Tablets from Ur designated UET3/01534 and UET3/01591 contain production records documenting daily brewing operations and output quantities that reveal the industrial scale of Sumerian beer production. The brewing facilities excavated at multiple Sumerian sites demonstrate specialized architecture designed to optimize fermentation processes and manage large-scale production operations. The brewing complex at contained dedicated structures with thick walls that moderated temperature fluctuations, elevated platforms that facilitated gravity-driven liquid transfers between processing stages, and multiple fermentation chambers that enabled continuous production through staggered batch processing. Archaeological recovery of brewing equipment included large ceramic fermentation vessels with capacities ranging from 50 to 200 litres, filtering apparatus for separating liquid from solid materials, and storage containers for finished beer products. The brewing procedures documented in administrative texts describe multi-stage processes that converted barley grain into fermented beverages through controlled operations requiring precise timing and careful monitoring. Tablet CBS 8563 from the University of Pennsylvania collection contains detailed brewing instructions specifying that barley grain should first undergo germination through controlled moisture exposure lasting 2 to 3 days, producing malted grain with enhanced enzymatic activity. The text indicates that malted grain should then be dried and ground into coarse flour, mixed with water at specified ratios, and heated to convert grain starches into fermentable sugars. Following conversion, the sweet liquid called wort should be separated from grain solids, transferred to fermentation vessels, and inoculated with fermentation agents. The fermentation control procedures demonstrate sophisticated understanding of factors affecting fermentation outcomes and beer quality characteristics. Administrative texts specify that fermentation vessels should be maintained at moderate temperatures away from direct sunlight, that fermentation typically progressed over 5 to 7 days, and that fermentation completion could be assessed through cessation of visible gas production and development of characteristic flavors. The texts describe addition of date syrup or honey to wort before fermentation, providing fermentable sugars that enhanced alcohol production and contributed flavor complexity. Chemical analysis of residues from brewing vessels excavated at archaeological sites has revealed remarkably sophisticated ingredient formulations and processing techniques. Analysis conducted by the University of Pennsylvania Museum identified residues containing barley grain components, date sugars, and chemical markers indicating fermentation by yeast organisms. The residues show consistent ratios of ingredients across multiple vessels from the same site, indicating standardized recipes that produced reproducible beer characteristics. The chemical signatures reveal fermentation conditions that produced alcohol concentrations typically ranging from 3 to 5% by volume, levels that modern brewing science recognizes as appropriate for stable beer products with acceptable flavor qualities. The quality control systems documented in brewing text employed systematic evaluation procedures that assessed beer characteristics including color, clarity, flavor, and fermentation completeness. Administrative tablets describe designated beer tasters who evaluated production batches and classified finished products into quality grades that determined distribution destinations. The highest quality beers were allocated to temple offerings and elite consumption, while standard grades served general ration distribution, and lower quality products were designated for animal feed or other non-beverage uses. The quality classification system enabled efficient allocation of production to appropriate uses while maintaining standards that protected institutional reputations. The standardization of beer products documented in ration distribution texts indicates that brewing operations achieved remarkable consistency in output characteristics. Tablets record beer allocations using standardized descriptive terminology that specified beer strength levels through a classification system, distinguishing strong beer containing higher alcohol levels, regular beer at standard strength, and weak beer with reduced alcohol content. The strength classifications corresponded to different ingredient ratios and fermentation procedures that modern brewing science recognizes as systematically varying alcohol production through controlled manipulation of fermentable sugar concentrations and fermentation duration. The economic integration of brewing operations within the larger agricultural system created complementary relationships that enhanced overall efficiency. Brewing consumed substantial quantities of barley grain, providing demand that supported agricultural production beyond direct food consumption requirements. The brewing byproducts, including spent grain solids, contained residual nutrients valuable as animal feed, creating circular material flows that maximized resource utilization. Administrative texts document systematic allocation of brewing byproducts to livestock operations, demonstrating integrated planning that optimized material utilization across multiple production systems. Archaeological evidence suggests that major temple complexes functioned as agricultural research centers where crop experimentation, tool development, and technique refinement occurred under priestly supervision. The systematic nature of agricultural advancement documented in texts indicates institutional knowledge development rather than random innovation. The temple complexes excavated throughout Mesopotamia reveal architectural features and artifact assemblages that demonstrate their function extended beyond religious activities to encompass agricultural experimentation and technical development. The temple complex at Nippur contained dedicated agricultural facilities, including experimental field plots with carefully controlled soil conditions, equipment workshops where agricultural implements were manufactured and tested, and libraries housing technical texts documenting cultivation procedures and experimental results. The integration of religious and agricultural functions within temple institutions reflected the Sumerian conceptual framework that viewed agricultural knowledge as divine wisdom, requiring institutional preservation and systematic development. The experimental field systems documented in temple complexes incorporated design features that enabled controlled comparison of different cultivation techniques, crop varieties, and soil management approaches. Archaeological investigation of the Inanna temple complex at Nippur revealed field areas subdivided into small plots measuring approximately 10 by 10 meters, each with independent irrigation systems enabling precise water management, and separated by permanent boundaries that prevented mixing of different experimental treatments. Administrative texts describe cultivation records maintained for these plots, documenting input quantities, treatment procedures, and resulting yields that enabled systematic evaluation of agricultural innovations. The crop variety testing programs documented in temple texts demonstrate systematic evaluation of plant genetic diversity that identified superior varieties for propagation and distribution to farmers. Tablets describe collection of seed samples from different geographical regions, cultivation trials comparing growth characteristics and productivity, and selection of varieties displaying desired traits including high yield potential, disease resistance, early maturation, and favourable grain quality. The testing procedures extended over multiple growing seasons to evaluate variety performance across different environmental conditions and to confirm stability of desirable characteristics across generations. The tool development activities documented in temple workshop records reveal systematic programs for improving agricultural implement designs and manufacturing techniques. Administrative texts describe fabrication of experimental plough designs with varying shared geometries, field trials evaluating performance across different soil, conditions, and iterative refinement processes that incorporated trial results into improved designs. The workshop facilities contained metallurgical equipment for experimental alloy development, testing apparatus for evaluating tool performance characteristics, and documentation systems that preserved successful innovations while recording failures that informed future development efforts. The soil management research, documented in temple texts, demonstrates systematic investigation of factors affecting soil fertility and crop productivity. Tablets describe experimental applications of various organic amendments at different rates, comparative trials of mineral soil treatments, and long-term monitoring of soil condition changes under different management regimes. The research programs incorporated controlled comparisons that isolated individual factors, enabling identification of causal relationships between management practices and productivity outcomes. The irrigation technology, development documented in temple records, reveals systematic experimentation with water management techniques and equipment designs. Administrative texts describe trials of different irrigation scheduling approaches, testing of various water application methods, and evaluation of canal design modifications aimed at improving water distribution efficiency. The experimentation produced innovations including improved gate designs for flow control, channel configurations that reduce sediment deposition, and water lifting devices that enhanced irrigation capabilities in areas where gravity flow proved insufficient. The knowledge dissemination systems documented in administrative texts demonstrate that temple agricultural research produced practical applications distributed to farming communities through systematic extension programs. Tablets describe temple officials visiting agricultural districts to demonstrate new techniques, distribution of superior crop varieties to farmers for propagation, and circulation of improved tool designs through temple-affiliated workshops. The extension activities created pathways for research innovations to reach practical implementation while providing feedback from farming practice that informed subsequent research priorities. The institutional continuity provided by temple organizations enabled maintenance of long-term agricultural research programs that extended across multiple generations of researchers. Administrative texts document hereditary priesthoods responsible for agricultural functions, with specialized training that transmitted accumulated knowledge from experienced practitioners to apprentice successors. The institutional memory preserved in temple libraries contained centuries of documented agricultural observations, experimental results, and technical innovations that provided foundation for continued advancement. Evening activities documented in texts include astronomical observations that served both religious and practical agricultural purposes, with farmers tracking celestial phenomena that influence planting decisions and seasonal planning. The integration of astronomy into daily agricultural practice demonstrates the systematic nature of Sumerian farming knowledge. The integration of astronomical observation into daily agricultural routines created systematic monitoring of celestial phenomena that informed both practical farming decisions and religious understanding of cosmic order. Administrative texts describe evening observation protocols conducted by farmers and priests that tracked stellar positions, planetary movements, lunar phases, and atmospheric phenomena, with observations recorded in tablets that accumulated into comprehensive astronomical databases spanning centuries. The astronomical record-keeping served multiple functions including agricultural timing, determination, calendar regulation, weather prediction, and religious ritual scheduling, demonstrating the multifaceted role of celestial observation in Sumerian society. The stellar observation procedures documented in agricultural texts focused on tracking constellation positions that served as seasonal markers for farming activities. Tablets describe that observation should commence at sunset when the first stars became visible, with observers noting which constellations appeared on the eastern horizon and which set in the west. The heliacal risings of specific constellations, their first visibility in the dawn sky after periods of invisibility due to solar proximity, provided crucial timing references for agricultural operations. The texts specify that the heliacal rising of the Hired Man constellation signalled optimal timing for spring barley planting, while the rising of the Scorpion indicated approaching summer heat requiring completion of grain harvest. The lunar phase tracking documented in agricultural calendars incorporated systematic observation of moon appearance and position that regulated monthly activities and determined timing for intercalary month insertions that maintained calendar alignment with seasons. Farmers observed the moon daily to determine lunar phase and noted the moon's position relative to specific stars that indicated its progress through the zodiacal band. The texts describe that certain agricultural operations should coincide with specific lunar phases, including planting during waxing moon periods, when traditional knowledge indicated enhanced germination and growth, and harvest during waning moon phases when moisture content decreased, facilitating grain drying and storage. The planetary observations documented in astronomical texts included systematic tracking of Venus, Jupiter, Saturn and Mars movements against the stellar background. The Venus observations proved particularly important for agricultural timing, with tablets documenting the 8-year Venus cycle that regulated certain planting decisions. Administrative texts indicate that Venus visibility patterns influence decisions regarding crop selection for upcoming seasons, with certain crops favoured when Venus appeared as morning star and different crops preferred during evening star appearances. Modern astronomical analysis has identified correlations between Venus visibility patterns and terrestrial weather systems that may provide rational foundation for these traditional associations. The weather prediction systems employing astronomical observations incorporated multiple celestial phenomena that traditional knowledge associated with approaching weather changes. Tablets describe that lunar halos indicated approaching precipitation within 2 to 3 days, that particular stellar visibility patterns correlated with wind direction changes, and that the colour and appearance of sunset skies provided forecasts of following day weather. Modern meteorological science has confirmed that some traditional weather prediction methods based on atmospheric optical phenomena contain valid physical relationships, lending credibility to ancient prediction systems. The agricultural implications of astronomical observations extended beyond immediate timing decisions to encompass long-term planning based on understanding of cyclical patterns. Texts describe awareness that certain astronomical configurations recurred at regular intervals, and that these cycles correlated with patterns in weather, crop productivity, and pest occurrence. The recognition of long-term cycles enabled farmers to anticipate conditions in upcoming seasons based on astronomical configurations, facilitating strategic planning of crop selections and resource allocations. The religious dimensions of astronomical observation reflected the Sumerian worldview that celestial phenomena represented divine communications requiring interpretation by knowledgeable specialists. The evening observation rituals incorporated prayers and offerings that accompanied astronomical monitoring, demonstrating the integration of practical and religious purposes within unified observational practice. The priest astronomers who specialized in celestial interpretation served both religious and agricultural advisory functions, providing guidance that integrated cosmic observations with practical farming requirements. The social organization of astronomical observation incorporated community practices that engaged multiple participants in collective monitoring activities. Texts describe that observation sessions often included teaching components where experienced observers trained younger farmers in constellation recognition, taught interpretation of celestial phenomena, and transmitted accumulated astronomical knowledge across generations. The communal nature of observation activities reinforced social bonds while ensuring preservation of essential agricultural knowledge. The consistency of agricultural techniques documented across multiple centuries indicates systematic knowledge preservation through family lines and institutional training programs. Apprenticeship texts describe multi-year training periods for farmers that ensured technical knowledge transmission across generations. The preservation of agricultural knowledge across the centuries of Sumerian civilization demonstrates remarkably stable transmission systems that maintain technical expertise despite political upheavals, dynastic changes, and periodic economic disruptions. Archaeological analysis of agricultural texts spanning from the early dynastic period through the III dynasty reveals consistent cultivation techniques, identical tool designs, and preserved mathematical procedures that remained essentially unchanged across 800 years. This continuity indicates that knowledge preservation systems functioned effectively to transmit accumulated agricultural wisdom from experienced practitioners to successive generations of farmers. The family-based knowledge transmission Systems documented in administrative texts describe hereditary farming families that maintain specialized agricultural expertise across multiple generations. Tablets from Lagash identify families by designations such as the barley specialist or the date palm cultivators, indicating that particular agricultural specializations passed from fathers to sons through direct instruction and practical experience. The hereditary transmission created knowledge lineages that preserved accumulated expertise while enabling incremental refinement through successive generations of practice. The apprenticeship programs documented in administrative texts formalized agricultural training through structured relationships between experienced farmers serving as masters and young trainees working as apprentices. Tablets designated AUCT 1/945 and AUCT 2/351 describe apprenticeship contracts specifying training duration, compensation arrangements, and competency, requirements that apprentices must achieve before completing training. The typical apprenticeship period extended 5 to 7 years, encompassing multiple complete agricultural cycles that enabled apprentices to experience the full range of seasonal activities and variable conditions affecting farming operations. The training curricula documented in apprenticeship texts incorporated systematic instruction in multiple knowledge domains essential for successful farming. Apprentices learned field preparation techniques including ploughing procedures and soil management, irrigation system operation and maintenance, crop cultivation practices specific to different plant species, pest and disease management strategies, harvest and processing operations, astronomical observation and calendar interpretation, mathematical calculation for area measurement and yield estimation, and record-keeping procedures for documenting farming activities. The comprehensive training ensured that apprentices acquired all competencies necessary for independent farming operations. The competency assessment procedures documented in apprenticeship texts employed systematic evaluation of trainee capabilities across different skill areas. Tablets describe that assessments included practical demonstrations of farming techniques under master supervision, mathematical problem-solving exercises requiring calculations relevant to agricultural operations, and oral examinations testing knowledge of cultivation procedures and astronomical timing. The assessments occurred at regular intervals throughout apprenticeship periods, with trainees advancing through progressive skill levels that granted increasing responsibility and autonomy. The institutional training programs documented in temple and palace archives supplemented family and apprenticeship transmission systems by providing formal education in agricultural science and administrative procedures. Temple agricultural schools trained specialists who served as agricultural advisors, research practitioners, and administrative officials managing large-scale farming operations. The curriculum documented in school texts incorporated advanced mathematical instruction, comprehensive astronomical training, detailed study of agricultural texts and technical procedures, and practical experience in experimental field operations. The institutional training produced agricultural specialists possessing knowledge exceeding that of typical farmers, creating expertise cadres who advanced agricultural practice through research and innovation. The documentation systems that preserved agricultural knowledge in written form provided crucial backup to oral transmission, ensuring that technical information survived disruptions in human teaching lineages. The agricultural texts preserved in temple libraries contained comprehensive documentation of cultivation procedures, equipment specifications, astronomical correlations, and mathematical procedures that could be consulted when oral knowledge proved incomplete or when innovations required documentation for distribution to farming communities. The written preservation enabled recovery of knowledge after periods of disruption and facilitated dissemination of innovations beyond the localities where they originated. The continuous improvement processes documented in agricultural records demonstrate that knowledge transmission systems incorporated mechanisms for integrating innovations while preserving proven practices. Administrative texts describe procedures for evaluating proposed agricultural innovations through controlled trials, documenting successful innovations in agricultural manuals and disseminating proven improvements through extension programs. The systematic innovation evaluation ensured that traditional practices evolved incrementally through validated improvements while avoiding adoption of unproven techniques that might reduce productivity. The remarkable agricultural achievements documented in Sumerian texts and archaeological evidence demonstrate that ancient farmers possessed sophisticated knowledge systems integrating astronomy, mathematics, chemistry, engineering, and biology into comprehensive agricultural science. The systematic preservation and transmission of this accumulated wisdom enabled Sumerian civilization to sustain dense urban populations through intensive agricultural production that required continuous application of advanced techniques across extensive farming territories. Understanding these ancient knowledge systems provides valuable perspective on human capabilities for developing sophisticated science through systematic observation and empirical testing, even without the theoretical frameworks and instrumental capabilities of modern scientific institutions. The evidence examined throughout this investigation reveals a profound truth about ancient agricultural capabilities that challenges conventional understanding of prehistoric human societies. The Sumerian farmers who worked the fields between the Tigris and Euphrates rivers possessed knowledge systems of remarkable sophistication that integrated multiple scientific domains into comprehensive agricultural practice. Their capabilities in astronomical observation, mathematical calculation, chemical processing, hydraulic engineering, and biological selection demonstrate intellectual achievements that conventional archaeological models struggle to explain through gradual independent development. The consistency and precision of agricultural techniques documented across 8 centuries of Sumerian civilization indicates that knowledge preservation systems functioned with extraordinary effectiveness. The transmission mechanisms employing family lineages, formal apprenticeships, institutional training programs, and written documentation created redundant pathways that ensured essential agricultural wisdom survived political disruptions, dynastic changes, and economic upheavals. The systematic nature of knowledge preservation suggests deliberate institutional commitment to maintaining accumulated expertise rather than casual cultural transmission of farming traditions. The sophistication of Sumerian agricultural science becomes particularly apparent when examining the integration of diverse knowledge domains into unified farming practice. The astronomical observations that determined planting timing connected seamlessly with mathematical calculations for water allocation, chemical procedures for soil enhancement, and biological selection programs for crop improvement. This integration indicates that Sumerian agricultural knowledge constituted systematic science rather than disconnected practical techniques, with theoretical frameworks linking observations across different domains into coherent understanding of agricultural processes. The textual attributions of agricultural knowledge to divine instruction from beings called the Abgalu warrant reconsideration in light of the documented technical sophistication. The cuneiform tablets consistently describe agricultural wisdom as transmitted rather than independently developed, provided by technologically advanced instructors who established the foundations of Sumerian farming practice. The physical evidence demonstrating capabilities that appeared fully formed rather than evolving through observable developmental stages supports these textual accounts more credibly than conventional models suggesting gradual human innovation. The implications extend beyond ancient history to contemporary understanding of human potential and knowledge preservation. The Sumerian achievement demonstrates that sophisticated science can develop through systematic observation and empirical testing without requiring the instrumental capabilities and theoretical frameworks of modern scientific institutions. The effective knowledge preservation systems employed in ancient civilizations offer models for maintaining essential expertise through periods of social disruption, technological change, and institutional transformation. The cyclical patterns apparent in human civilizational development suggest that advanced knowledge systems have emerged, flourished, and declined multiple times throughout prehistory. The Sumerian agricultural science may represent preserved fragments of even earlier knowledge systems that survived catastrophic disruptions through careful institutional preservation. Understanding these cycles and the mechanisms that enable knowledge transmission across catastrophic periods becomes crucial as contemporary civilization faces challenges including climate change, resource depletion, and technological risks that threaten continuity of accumulated human wisdom. The systematic agricultural knowledge documented in Sumerian texts demonstrates that our ancestors possessed intellectual capabilities fully equal to our own, achieving sophisticated science through patient observation, careful experimentation, and systematic documentation. Recognizing the true extent of ancient human achievement challenges the narrative of linear progress that dominates conventional historical understanding, revealing instead a more complex pattern of cyclical advancement, where knowledge accumulated through institutional effort can persist across millennia or be lost within generations depending on the effectiveness of preservation systems. As we stand at a historical moment where crucial agricultural and environmental knowledge faces potential loss through erosion of traditional farming practices and disruption of knowledge transmission systems, the Sumerian example provides both warning and inspiration regarding the fragility and resilience of human wisdom across the vast span of civilizational time.